This is an outline of a first-hand investigation that was done to investigate, gather information and analyse data, finding things like final velocity, maximum height reached, range, time of flight for different situations. But this particular one involved a ramp down onto a tabletop and a flat tabletop. A ball was rolled, and over a period of 1 metre the ball's velocity was determined, and this was the initial velocity in the x direction. That was just done by working out the velocity equals the distance divided by the time taken, and it was 1 metre, and from memory I think it took almost 1 second. So initial velocity was approximately 1 metre per second. Then the ball left the table and proceeded to carry out its projectile motion, hitting the floor, and we had to work out from the point where it left the table at the top of its flight the distance or the range delta x. And we had other information we gathered, such as the height of the table, delta y. We have initial velocity. So we had quite a bit of information ready to do an analysis. We also knew that gravity in our room is approximately 9.80 meters per second squared. So using two particular formulas from the projectile range formulas, delta x equals ux t, that comes from the formula v equals d on t, d equals v times t. So we've got distance, velocity and time. Now we can work out exactly before the experiment where our range will be, where the ball will hit, and that was the idea. So we combined this equation here with another equation, which was delta y equals uy plus ay t squared, and the t in this case was the change in time. So we can rearrange this first equation to give us a value for t, and we get t equals delta x on ux. We put this value for t into this formula here. We get delta y equals 1/2 ay delta x squared on ux. We can also get delta square root of 2 delta y on ay times v. And this is, vx. This value here was the value for t. Okay, so we can use that formula, find out from our tabletop trials we want a set of results, and we're trying to find the initial velocity in the x direction, and we worked that out from averaging a variety of runs across the tabletop and finding the average velocity, and it's usually around 1 meter per second depending on the speed from the ramp. Our tabletop was approximately 1 meter high, but that tabletop height is measured, and that's your delta y. So we find our range and we put a cross on the carpet to mark the range we expect. We then do the experiment several times and see where the ball did in fact fall, and if the predicted landing spot was the same as the theoretical or actual landing spot. Once we have several measurements, we can determine the time of flight. And we can use several equations for that one, but if we find that's the distance the ball travels from the bottom of the table to the landing spot is our range, or half our range. We can find out using this equation for range equals ux t equals range on ux, and we can find out the time of flight. For reliability, we repeated the velocity trials on the top of the table. Rulers, timers as accurately as possible, and that's using millimeters on the rulers, avoiding parallax error, using the ruler and putting your eye at the level of the ruler and making your reading, rather than looking down and making a reading. We could have also used a data logger and motion probe to determine the actual initial velocity across the table as it left the table and began its projectile motion. The data logger collects the information and it's stored in a computer where we can analyze the information and do graphs and other things with the data. The data logger collects information from the probe and passes it on to the computer.